Okay, hello everybody. My name is Levente Meszaros, and I'm a member of the OMNeT++ core development team. And in the recent months, I was working on a new unified, scalable, and extensible physical layer for INET. It's an ongoing effort. It's incomplete yet, but in this presentation, I'm going to talk about the motivations, the goals, and the difficulties and the results that we achieved in this period. Okay, so the motivations. Currently, there are two widely used physical layers. One is in the INET framework, and the other one is the Mixim framework, which unfortunately are quite incompatible in certain ways. For example, they process different control info objects, different commands. They have different public C++ APIs. They give different indications. So practically, it's pretty small. The interface is pretty small that is shared between them. Then there's also another problem regarding scalability, because they model the physical layer on different levels. So the Mixim framework is much more detailed than the INET physical layer, but it's really hard to just switch a parameter to switch to the other framework because of the incompatibility. You can't just say that I have a model here, a simulation, and I want to model the physical layer, let's say, less precisely or more precisely. And there's this other issue about extensibility. If you want to implement something new, some new feature, you have to make up your mind. There's a dilemma. Where would you implement it? In Mixim or INET or both, or create a new one? Maybe it's in inverse. And there's also maintainability. There are functionality in both frameworks implemented in both of them. For example, the neighbor management that is responsible for managing the list of neighbors accessible from radio. It's part of both frameworks. You have to manage the code in both frameworks. If there are bugs, if there are new feature requests, and same problems appears, the duplicated functionality. And there are other functionality which are missing. It often comes up. For example, we will need to be able to simulate directional selectivity in antenna models, orientation, or what about bit-precise physical layer models, where the actual symbols might come up and more precise physical layer indications are needed. And finally, there's again the power hardware support. You know, nowadays computers have quite often 4 to 6 processors, and there are even GPUs have hundreds of processing units, and we don't use that. And the physical layer is dealing with a problem that is highly parallel. That's what nature does pretty well, but our software is not that good at. So these are the motivations, and it sums up as the following goals. The first goal is about how we want to keep all the functionality present in both frameworks. So the new physical layer should not lose anything that is already implemented. In the sense of functionality, I'm not talking about the source code. And we also want to make the new model scalable in terms of level detail regarding with respect to the processing and representation, signal representation. Because as I mentioned, that they have different signal representation. And we also want to introduce new signals representations like the unit disk radio, or even more precise representations that is bit precise. And we also want to make the model extensible, to make the model more modular and less monolithic, like the INET model. That means we want to allow the user to focus on certain parts. If someone wants to implement a new, let's say, propagation model, then he has to be able to focus on that part, and that model should be usable independent of the analog representation, for example. And of course, then we need to port, if we change the physical layer, the public interface of the physical layer, then of course we need to port the higher layers from both frameworks. That should be hopefully not that difficult. But as I mentioned before, that the public interface is incompatible, so if we come up with a new one, then there's this other problem. And the last one is the most difficult, but can we support parallel execution? And in this point, I'm not talking about generic parallel execution. It's not a solution for the generic problem. It should be a specific solution for the physical layer, because it's a embarrassingly parallel problem, computing all the receptions and all the interference at all radios all the time. So it's really a parallel problem as it's in itself. So can we provide a specific solution for this problem? Okay, about scaling. Well, in simulation, it's always about performance versus accuracy. It's a difficult trade-off, because we have just finite time to simulate. So we identified four different axes where this scalability can be controlled. The first one is about the architecture of the model. Where architecture is about the model, whether it's statistical or even more simple than being statistical, like the unit disk radio. It's not even considering the transition power. Or the other end is the emulation, where we can really talk to the real hardware. In terms of architecture, we can go from flat to layered. In a flat architecture, it's not modular, it's monolithic. But in a layered architecture, there are probably more components taking more memory, more time, more data conversion, more data management, resource management, allocation, and so on and so on. As for the data axis, on the one hand, there are scalar data. For example, you could say the transition power is a scalar number. You have a carrier frequency and a bandwidth, but already on the other end of the spectrum, there's a dimensional data that is used by mixing. It's a quite complicated data representation, multidimensional in terms of space, in terms of time, frequency, and even space, for example. And then there are the number of messages that the simulation kernel has to handle, because as the communication goes on the medium, we can reduce the number of messages sent as an extremum to 1, where only the desired destination node gets the message. And of course we lose accuracy, but it depends whether that accuracy depends on the simulation, whether that accuracy is desirable or not. And on the other end is then everybody gets everything, and everything is computed very precisely. So this is about the scaling. And about extensibility. For being more extensible, we would need to, or we split up the modules into further submodules, so that they can be replaced. The different parameters in different implementations don't get mixed up. For example, in the radio module in the old INET implementation, a lot of different implementation parameters mixed up, so it was really hard to figure out which parameter belongs to which part of the implementation. So here you see there's a radio module that's split up into 4 submodules. The antenna represents, of course, the antenna. It is responsible for the directional selectivity. We also separated the transmitter and the receiver part. This even allows asymmetric simulation in terms of, for example, accuracy, but also, for example, in one direction you could use different parameters than in the other direction, for example. And then the separate power consumer model that is optional. That is also can be replaced, because it might be required for a certain simulation. And then the medium is also split up into a propagation model that is responsible for computing signal propagation through space over time. And there's this path loss model, which is responsible for the power reduction as the signal propagates through space. And the obstacle loss model is responsible for the power loss as the signals propagates through the physical environment. And the multipath model, which is responsible for computing multiple passes, either stochastically or other ways. And noise, there's background noise, and there's this neighbor component which is responsible for efficiently computing the potential receivers for transmissions. And the arrow represents that all the transmissions, all the communication goes through the medium, so it's a central component. That's why it's a good candidate for parallelization and optimistic background processing. Okay, and this slide shows the so this slide shows the data flow in the framework. Okay, the blue boxes represent data, and the red boxes represent processing components. So the physical layer gets a MAC frame from the MAC layer, and along with the transmission request, which is basically a control info representing the requested physical properties, like transmission power, for example, and then produces a transmission, which is a data structure that describes only the transmission itself, that is immutable. It holds all the properties that describes the signal that is transmitted to the channel or to the medium. And there's this propagation model which combines the mobility of the receivers and the transmission and computes the potential arrival data. This needs to be done immediately because we need to schedule the messages during the transmission. And then the rest of the computation happens in the future or parallel in the background if parallel computation is done. Attenuation is basically this component combines all the power losses, path loss, and multipath components, and computes the reception that describes how the signal arrives at the receiver. It's an immutable data structure. It's independent of any other transmission that is put on the channel later on. Even if that future transmission would interfere with this reception, this is independent of that. And then the receiver takes the interference that the medium computes from all the receptions that interfering with a single reception, and then the noise, and the listening mode the receiver that describes the way the receiver is listening on the medium, and then produces the reception indication that is passed up as a control info to the MAC layer. So this is basically a bird view of the data flow in the new physical layer. The transmitter and the receiver is optional. It can be further split up. It's the well-known layers: the packet domain, the bit domain, symbol domain, sample domain, analog domain. If you look at the old INET model, basically it only contained the analog domain representation of the signal, and from the bit domain it contained the bit lengths, and that's all practically. So we are also planning to have this layered architecture, but this is optional. So this is not because it puts extra effort to be. So it's extra to compute all these things. It means more data processing, data conversion, and so on. So it's just an optional if someone wants to have that kind of data. It's also true for the signal representation. A flat representation means less memory allocation, memory management, and with the while a layered architecture means separate classes for each one of them. Here are a couple of things that could be present in the data structure and signal representation in various domains. And this is why I mentioned that in the old INET model, practically the space-time coordinates and some scalar value the bit length was present, while in the MIXIM model we have this dimensional data, dimensional transmission power or bit rate or etc. And basically nothing else. Yeah, this list also includes the indications, the physical indications that goes upward, like the bit error rate and symbol error rate, or receive strength indication, signal strength indication, or signal to noise and interference ratio. And here are the currently 4 supportive analog domain signal representations. The first one is the simplest. It's basically the unit disk radio, which describes a signal with three ranges: the communication, interference, and detection range. And of course, communication is possible within the communication range as long as there's no interfering signal within the interference range that overlaps also in time. It's very inaccurate, this model, but this model might be absolutely enough for a routing protocol, because for a routing protocol you don't need to precisely, or not even precisely, statistically simulate the physical layer. It's enough if some signals get lost and some can go through. Okay, this other representation is the old INET representation. It's what I call scalar signal representation, and the bottom two ones are present in the MIXIM physical layer that uses the complex mathematical structures present in that framework. So I took them over in the new implementation, and the first one is the ultra wideband model, and the other one is some imaginary model where one can use complex data structures. I didn't draw it in a way that it shows that it could change over time too, but anyway, you can imagine that the multi-dimensional data can represent, and these representations allow crosstalk, for example. So you can have the new physical layer. You can, if multiple Wi-Fi channels are used, then you can simulate crosstalks, or even different protocols could interfere with each other. And here's just a quick sketch about message processing, where the important point is where the parallel computation could happen in theory. This is the dashed lines represent function calls, while the solid lines represent the message sent, and it shows that all data processing goes through the medium, the central component, so that it gives a chance to pre-compute them. But actually, the real reception, of course, happens in the receiver, because it has to be extensible and modular. So you have to be able to replace it. And we also took over the MIXIM model so that the reception happens in multiple phases. It doesn't have to be one single step, so it can further process the same message depending on the level of detail of the accuracy of the model. This one shows the axis, the trade-off between accuracy and performance with respect to the number of messages sent on the medium. For different filters, the range filter, which means that if the receiver is outside of the communication range, which might be computed by the maximum transmission power and based on the maximum transmission power and the minimum reception power, and on the path loss model of the channel, so you don't have to send frames there, because I forgot to mention that the interference is computed by the medium, so it doesn't matter if the message is not sent there. Other messages will still be interfered by this transmission. Or there's another opportunity: if the radio is not in the receiver mode, of course it doesn't have to get the message, because it might be transmitting. or it might be sleeping, depending on the Mac model. Or it can listen in a different mode on the channel, a different carrier frequency or different modulation, which means it's impossible to receive successfully that message, so it's really useless to send it to the radio. And finally, the MAC address filter, if for example, the MAC address is different of the receiver than the destination that is in the packet, then it might be useless, or it might be beneficial to skip those kind of messages. It might decrease the accuracy of the simulation, but because some Macs, for example, in promiscuous mode, might need to receive all those messages, even if the MAC address is different. So it depends on all what we want to achieve here is to give the opportunities for the user. So give the parameters so that you can fine-tune your simulation between performance and accuracy according to your needs. So that's it. And here's this para execution thing. So I repeat that this is not about the general solution of parallel execution. We don't deal with look ahead here. Actually, the opportunity comes from that there are lots of receptions that need to be computed, and it's also true they dominate the performance of the physical layer. So if there's a lot of radio is communicating, and there are a lot of messages, and it's pretty easy to compute how quickly it scales with the number of transmitted messages and the number of radios, the required number of computations. And they are mostly independent of each other, which is not quite true, but anyway. And here are the options that we can use: parallel hardware from multi-core vector instructions, and also from for GPU. For the GPU case, it's pretty easy to come up with one very simple case is to compute the arrivals. So when a transmission happens, there can be like 1,000 receiver nodes, and the GPU has 500 processors to compute the square root of the distance and compute the distance and the propagation time and all that stuff. So it can be much faster than computing on the main CPU, depending on the number of radios and communication or transmissions on the channel. So all this optimistic parallel computing in the background threads is useful only or efficient only if the receptions are mostly cached by the medium by the time the receiver will actually need them. And of course, we also need to be able to discard results and already computed the results because when new transmissions enter the system or enter the channel, they might invalidate the previously computed reception indications, but not the receptions itself, because they can be, for example, they are immutable and they can be reused. And here comes an interesting and somewhat difficult problem to solve, because this is different from the generic parallel simulation in that here we need to recompute the same results several times. And why we use random number generation there, it means that it's not only that the parallel simulation will not produce identical results to the sequential ones, it will not be deterministic unless we can ensure that the random number generators can also be reset or by some other means. Okay. So it's different from the generic case, but it's doable. And there's this new physical environment model. The old model was replaced by this one. It includes certain 3D geometric classes that is needed for properly represent 3D objects with 3D shapes and positions and orientations. And the objects can have graphical properties, and they actually appear on the canvas. Can be initialized from XML if you have lots of data to be loaded. And there's also an efficient object cache for intersection for path loss. that is used by the obstacles. No, it's not path loss, obstacle loss. And there's a new feature called visualization here. You can see a transmission. This red circle represents the arrival of the first bit to this host. And there's also the recent the movement trajectory is shown here. It shows the recent movement of the node. This black line. And for example, the blue lines shows the successful transmissions, and you can even see the intersections through the obstacles. These are 3D objects. We're just looking from the z-axis. This is thanks to the new Canvas API that is introduced in the OMNeT 4.5. There are some notable changes in the C++ source code. For example, the physical quantities are compile time verified by the compiler. So it was quite confusing that sometimes it was milliwatts, then sometimes it was watts. So it's easier, it's safer this way. And it also, this C++ template library also handles arithmetic expressions and operators, so it properly handles the physical units, so the calculation is correct. It checks this in compile time. It's not easy to handle the error messages, but it's still beneficial, I believe. And the extensibility, it's achieved through polymorphism and subclassing and virtual functions. And I also introduced a lot of pure virtual interfaces to be able to show the required interfaces that need to be implemented by certain components, not just overriding whatever function you think you want to, but it's easier to see. And for parallel execution, we need a lot of immutable data structures and purely functional code that is free of side effects, so that we can run them in parallel safely without race conditions and things like that. Okay, here are a couple of functionality implemented in the radio. We took over the radio modes from Mixim and introduced a new one, transceiver radio mode, which allows the radio to be simultaneously in the receiver and transmitter mode using the same antenna. There are cases where it's useful. And there are the directional antennas. It's some trivial models yet, but we have orientation support, full orientation support and directional antenna support. And then this is the unidisc radio and the INET compatible and the Mixim compatible analog signal representation. And then we also separated the power consumer model, which also has a separate interface, so you can replace it as long as you keep the interface implemented. It's currently based on the radio mode and the transmitter state and the receiver state. The transmitter state is either transmitting or idle. The receiver state is either idle, busy, or synchronizing or receiving. And ported the standards. That means I just updated the code, ported the code from INET and from Mixim, so that they work with the new physical layer properly. Regarding the medium, there's 2 propagation models right now: constant time, constant speed. It's really all the path loss, not all the path loss yet, but most of the path loss from both frameworks have been ported. And then we have a straight path-based dielectric and reflection loss for obstacle loss. And then we have 3 different neighbor cache implementations. It's unclear in certain situations one is better than the other, or vice versa, so it's unclear which one is the best. And we have a couple of geometric classes, and this is mostly for orientation support and for the obstacle support in the physical environment model, and some algorithms that is needed. It's not so interesting. It's just so that it's reusable, so if you want to use it for something else. And then, of course, we need some mobility that can be used for orientation. And also the power model was also replaced. The old power model was replaced by a new one that also has a separate interface that can be replaced with alternative implementation and works well with the other parts of the system. And the physical object cache is also efficient intersection computation, bounded volume hierarchy tree and spatial grid. Some higher layers have been ported from Mexim. The CMSA, BMAC, LMAC. We also did an IDEA MAC, that's 3 LMAC. If you're implementing or simulating a routing protocol, it might be sufficient to use an IDEA MAC and the unit disk radio, because you're not interested in the details in the physical layer. And some network layers. INET network layers, they are untouched. They work as this. And there are some new functionality under development. It's a layered radio that also simulates the forward error correction and things like that. It's a bit precise representation, and there's another branch, for example, to integrate the GNU software-defined radio, so it could actually talk to the real hardware. And the multi-threaded or the GPU-based medium, that is a parallel medium. GPU-based scalar medium means that actually the scalar analog signal representation can be used in a way that most of the reception can be computed on the GPU parallelly. And the GPUs, can have 1,000 cores, so it's not something true. And of course, the medium is almost generic enough to be used for wired mediums and also for acoustic wireless, for example, where the propagation speed and the speed of the mobility of the nodes are comparable. So you might need some receiver movement approximation during the transmission, because it's not like comparing the movement of a car to the light of speed, to the speed of light, sorry. And some less interesting things. Multipass fading is currently under development. It's in flux yet, but there are possibilities for ray tracing reflections, so that radios can receive correctly messages via refractions, not through the direct pass properly. Tests and examples. During the development, I focused on being compatible with the old INET implementation with respect to all the fingerprint tests. If someone doesn't know what the fingerprint test is, it is a simple hash computed of the simulation trajectory that includes all the timestamps and module IDs and things like that. So it's quite sensible. If something goes wrong, then probably the fingerprint will be wrong. So it passes all the tests, so it's not worse than the previous implementation. Although there were certain bugs found in both, by the way, by comparing the fingerprint tests. And then we have some unit tests for the corner cases and some new examples that shows, for example, the different physical layer parameterizations with various MACs or some other things. That's not so important. And here's a short demo. This is two nodes are communicating sending with some ARP requests, and you can see that the red lines that the obstacle blocks the transmission, and why finally this one is successful, and then it answers with a reply. It's again, this animation is thanks to the new Canvas API is pretty simple. So it's like, I don't know, it's like 50 lines in the code. So it's really nice to have this. Thank you for your attention.
I have one question. I'm still wondering, how did you implement the channel, the medium, as you call it? it's a singleton pattern, or for each node in the network you compute the whole?
No, it's not a singleton in the sense that you can have multiple mediums in a simulation if they are, by some ways, you want to, if they are separate in a way like they're far enough from each other. So it's not a singleton in that sense, but in the sense that being a central component, radios, I mean the transmitters, radios, knows which medium they are on, and all the communications go through on that medium. But that's just, it's rather a C++ architecture thing. It's not. It doesn't mean that the actual messages go through the medium. So the OMNeT++ messages go from radio A to radio B, but the medium knows before the message actually gets sent. The radio knows the transmission is put on the medium. Does that answer your question?
Yeah, but I'm just still wondering which are the advantages, because you said you want to use the GPU. So if for each receiver you have to use the GPU when you are resetting something, that would be also increasing the cost in the computation, I guess. Because you have to talk with the GPU, collect the results.
Yes.
To the next,
it depends on the number of transmissions and the number of radios, whether if it verse it or not. So it's going to be a parameter. So it's just an opportunity for the user to control whether if you want to compute, for example, the arrival times using the GPU, or you let it be computed on the CPU. That's normal. Then there's nothing new.
Well, this is partly related to my work, so
Okay.
I thought that it could be improved, this kind of way of dealing with the receptions, if the channel model could be a central component, a C++ component, that somehow collects all the possible links between the transmission and the transmitter and the receiver.
Yeah.
And
It does.
the next 10, 12, 20, 40 sequence or events, sorry, they can be computed parallelly in the GPU. So
It
you
does.
just deal with the event scheduler from OMNeT, and you use somehow the idea of the Horizon project in order to parallelize it and to speed up the computation, instead of dealing one by one.
I'm not sure if I understood right, but it actually does parallel computation. Currently, it's under development, but it does it in a way that in the background thread. So the idea is that we want to block the main thread as little as possible,
Okay.
and as soon as possible, the main thread just creates the transmission, gives it to the medium, and continues simulation, because who knows what's going to be the next event, next 100 event. And in the background, the medium is responsible for computing all the receptions and all the interferences. But what is important is that the medium has to be ready only with the next reception in the queue, because that's going to be the next one. So before, I don't know if answers for your question.
Yeah, you might have some interferences you have to deal with them.
Yeah, it has to deal with that. It has to deal with that. And if new transmissions come into the medium during the background processing, then of course it invalidates certain results. But that's why there are some results which are independent of that. For example, the reception, how the signal arrives at the receiver, is separate from the interference. So it doesn't matter if new transmissions come into the medium, because that computation doesn't have to be repeated.
So maybe we move this offline.
Ah, yeah.
I have one more question here before we have to move over again some concrete.
Related question to the GPU. How do you access the GPU? What is the language, and how do you...
I use the NVIDIA GPU with CUDA, CUDA.
You do CUDA, yeah?
Yeah.
And that means you have double code for this
Yes.
reception? And,
For certain parts, but these parts are really small parts. That's why the architecture is modular in a way that you don't need to re-implement just only those parts which are really needed to be re-implemented, because they can't reuse the code.
Why not OpenCL?
Well, OpenCL is possible too. I just decided to use the NVIDIA library because it's very in the early phase on that part. So I just wanted to look at it, whether if I really get some performance out of that. It turned out, I can give you some random numbers, but this is just prototyping, so that physically I can easily be 10 times faster,
Sure.
depending on certain parameters. And, yeah.
Perfect. So we move discussions next door, I guess, to some coffee, and then we're back at 3 p.m. for the exercise.